Welcome everyone to Soil Science Principles. Okay, here's a few fun facts about soil. Did you know that almost every single plant on Earth requires soil? Out of the 391,000 species, there are a few that can live without it, such as bromeliads, which include things like air plants. We call these epiphytes, and they require water only, and most of them get their nutrients from rotting leaves and other organic matter that falls down or washes around the plant. Then you have some water obligate plants like lilies that get their nutrients from the organic matter floating around in ponds, etc. There's a hint right there. Apparently organic matter is a key player for nutrients in any plant. Here's a picture of an Andean bear from South America getting ready to eat some bromeliads, which is their primary food source. You can see the plants attached to the trees, and they're certainly not in the soil. You know, we look at a pile of dirt the same way we might look at other things across our landscape, but we never stop to think, what has that dirt seen? How long did it take for it to form? That pile of dirt or soil might have originated thousands of miles away and taken millions of years to grind itself from stone into that pile of thin particles. Over thousands and thousands of years, all kinds of external and internal pressures transform what we call parent material into different sized and shaped particles. Those are mixed up with organic matter, bugs, and water. For those of you that live in glacier country, you can look across your landscapes and see millions of pounds of soil being formed right before your eyes. The mountains might be the parent material, but as gigantic glaciers of ice retreat from North America, and they still are, they scraped the sides of these huge mountains only to leave a trail of ground-up soil. Later, it'll become part of the forest down below as it's washed away, or even part of our rangelands. Much of what we call alluvial soil, or soils that are deposited by surface water, becomes some of the more productive lands for grazing animals and farming. Watch this video clip and pretend that you're a rock on its way to becoming soil. So, how is soil made? Well, it's driven mainly by weathering. Again, rocks and minerals are bashed and ground and begin to disintegrate and decompose into smaller pieces. Now, there's two types of weathering. The first is purely physical, mainly caused by water, temperature, wind, and even plants and animals. This is called disintegration because these activities cause parent material to fall apart. Then there's biogeochemical weathering, which causes decomposition through water, oxygen, and organisms. It's kind of like leaving something outside for a few years in New Mexico. It'll start to look like my dad's truck that's parked out in the arroyo. On the left, you can see the bedrock begins to disintegrate and break down very slowly. As it's broken down into finer pieces, organisms are able to live there and survive. On 3, we add the organic matter. Over time, mineral and organic matter mix and build up, creating layers that capture water and nutrients that are then available to a greater diversity of plants. The process of organic matter buildup continues, resulting in increasingly complex systems. While soil formation is driven by weather processes, ongoing soil development is largely driven by plant and animal soil interactions. And let's not forget human land use. Soil scientists and ecologists pretty much focus on the developmental side of things and have categorized soil into horizons. These are layers of soil that are distinctly different in color and texture, physical properties, and composition. The O horizon is the top layer of soil that's made up of dead organic matter, like leaves, bugs, sticks, and poop, and that are in the early stages of decomposition. Sometimes you'll hear people call it litter. The A horizon is the dark-colored top layer of soil that's made up of decomposing organic matter and soil microbes that are farther along and start to look like real soil. This layer has a lot of biological activity because of the microbes that are breaking down the organic matter. This This is what I call the high-fat layer of soil. Its nutrient content and water holding capacity in this horizon is much higher than the other layers. The B horizon is the layer that's lighter than the A horizon, usually with different shades of brown. There's much less organic matter and a higher degree of salts and clay particles as water filters through, causing the breakdown of soil particles and leaching. And the C horizon is derived from weathered bedrock and is known as the parent material. This provides a source of mineral content for the upper horizons. I wanted to mention that there's another layer, the R horizon. It's often classified as bedrock, and it's down below everything else. I sometimes have a tough time seeing the visual difference between the C and the R horizons, so keep that in mind, but the C horizon should have some weathering. So looking back at this graphic on the left, you can see the translocation, mixing, and churning of soils that goes on. Different layers provide different components for other layers. As the C horizon is weathered by water infiltration and starts to break down, it floats minerals up at the top layers, and microbes help to mix the parent material up into the B layer. Some of it gets into the A layer, so even though these arrows are pointing down, and though that's the kind of directional flow of it, some of those materials do move up in the layers as well. Soil color is determined by mineral content. Sometimes these layers are super noticeable. If you've ever dug a soil pit, you can often see them pretty clearly, but some areas are easier than others. I like to call this the soil horizon butter churn because you can see the mixing of layers under healthy conditions. Under unhealthy conditions, there would be little organic layer and mixing, and probably a lack of water filtration that assists with the movement of materials. While most groundwater is impacted by the A and B layers, those of us in the West also need to be concerned with what's going on in the C layer, given the water capturing capabilities. Some water tables are super deep, and all are impacted by these soil horizons. This graphic's kind of cool because it also shows some of the services that are provided by these soil layers. Biological diversity, pedological features and soil classification, and then urban land use, groundwater protection, and rock weathering. The mineral content comes from all of that ground up bedrock. Organic content, often referred to as soil organic matter, comes from dead and decaying plants, animals, and microbes. Although it's a small fraction of the soil, it's probably one of the most important for nutrients and the stability of the soil structure. The air and water content of soil fluctuate depending on the soil type and the wetting and drying of soil. Here's the famous soil triangle. You can see that between the three soil types of sand, silt, and clay, there are combinations that make up clay loams, silt loams, and sandy loams, and each is important for different land uses. You'll learn more about this in our next video lesson on soil quality indicators, but let's go through each soil type. 1. Sand. Smaller particles than 2 millimeters but larger than 0.5 millimeters. Sandy soils have really large pores that allow water, nutrients, and air to move freely. Silt, the particles are smaller than the sand, but larger than 0.002 millimeters. It's pretty amazing that somebody's actually measured all that. It holds much more water than sand because of the smaller pore size. And then clay, you have really tiny particles, and they're very strong with their ability to absorb water and nutrients, but sometimes they hold on to the water too tight, so it makes it really sticky. We've all been here at one time or another. All right, let's look at soil structure. That plays an important role in soil function. Most soils have some sort of aggregates in size and shapes that help to identify their different soil orders. You can take a look at those on the right. All right, now let's talk about soil orders. These are characterized by their geological influence, and there's 12 of them. They include all of the soils on the Earth. Don't memorize these, but you can find out through the USDA NRCS Web Soil Survey what's in your area, and that will be important. I always thought it'd be really cool to identify each one of these, so on my travels around the world, people would be super impressed by my knowledge. So far they haven't been, just with the other stuff that I know, so I haven't put much time into it. If you do want to memorize them, I'll post a link so you can review them. Sounds like another fantastic family outing activity that will make the kids want to put the iPads down. Right. Now this map is pretty cool. The NRCS put it together for the 12 soil orders, and you can see here that for the US, we pretty much have 4 orders in the lower 48 states. The iridosols, the mollisols, the andisols, and the ultisols. I guess the gelisols occur only in Alaska. Here's a graphic illustrating the distribution of the different soil orders within the US. I guess they left the gelisols out. You can see here that the Great Plains and our more fertile farming areas coincide with the mollisols. Now these soils were created mostly by the glacial activity that we talked about earlier. Unfortunately, their productivity is what's resulted in our prairies being converted to croplands in the post-colonization era. The iridosols, well, I've pretty much lived with that order most of my life. They're a product of aridity, or hot and dry conditions, and they're found in Nevada, Arizona, and New Mexico, where water is limiting resource. There's minimal to no leaching, and therefore they accumulate a lot of salts and calcium. There's little to no organic matter, so annual growth is pretty meager. However, the plants that do grow on these soils are highly adapted to these conditions, as are the animals and people who have lived there for thousands of years. Then we have the ultisols. Those are exposed to high amounts of precipitation, so they're highly leached and are heavy in clay. You'll see their vegetation is mostly hardwood and mixed conifer forest with high acid soils. And then we have the andisols that are high in volcanic matter and are up in Oregon and Washington. Okay, we've made it over the mountain. That's a lot of information, but it really is interesting, especially when you realize how much it impacts all of the other things that we're learning about what live on the soil. One of our class activities will be digging a soil pit. That may sound kind of strange and tedious, and what the heck are people going to think if you're out in the middle of nowhere digging a big hole? Just be sure to ask a tribal officer, can you dig it? Sorry. But I will say, if you're going to work in a specific area for a while, digging a pit will be super helpful as a reference. It helps you know your soil better and get a good look at all the stuff we've been learning. You'll be able to identify the horizons, look at root growth, and you can introduce yourself to your earthworms and microbes and see what's going on with leaching. Don't worry, if you're under COVID restrictions and one of the rules is no digging big pits outside, we'll set it up so you can do the exercise using some photos. But you might want to tell the tribal officer again, or they might think you're looking at dirty pictures. Sorry. Okay, go grab yourself a coffee and watch these elephants. Until next time, take care.